Hello everyone, welcome to the presentation on how functional programming is transforming the field of meteorology. My name is Dimitope Sochije, and today I'll walk you through how applying functional programming principles to weather modeling can result in cleaner, more scalable, and more efficient systems. Let's get started. Weather modeling today faces significant challenges. A prominent example is the Global Forecast System, which contains over 2 million lines of code. This leads to what's often referred to as spaghetti code, highly complex and interwoven logic that's difficult to untangle. With so many contributors and interconnected modules, the code becomes a nightmare to debug. The shared state and mutable data structures make it nearly impossible to isolate errors or make meaningful changes without unintended consequences. However, Par- parallelizing these models is challenging. Shared states create dependencies, making it hard to divide the workload across multiple servers, leading to inefficient simulations. These are seriously limitations in an age that we need faster or more accurate forecasts. Let's talk about functional programming. Functional programming offers a refreshing alternative. Unlike imperative programming, which relies on changing state and executing commands in a specific order, functional programming is centered around pure functions and immutable data. Pure functions always produce the same result in the same input with no side effects. This makes programs more predictable and easier to test. Data mutability ensures that once a data structure is created, it cannot be altered, eliminating many sources of bugs. Instead of telling the computer how to do something step by step, we describe what we want done in a declarative style. This result is cleaner and more maintainable code that's easier to reason about. Let's look at some core concepts. For example, pure functions. These are like the heart of functional programming. No hidden state, no external effects, just input and output. That predictability is vital in complex systems like weather simulation. Let's also look at immutability. By not allowing changes in existing code, we can make our code safer. There's less room for bugs caused by unintended modifications. And then we have high order functions. They are flexible, reusable, and code blocks. They enable code to be both flexible and reusable, which is incredibly helpful for processing large data sets in meteorology. Now, let's look at some case studies. Our first case study is data ingestion and cleansing. Weather stations, satellites, sensors produce massive amounts of raw data, often in inconsistent formats or with noisy readings. Using informational techniques, we can build data pipelines that apply transformation and validation steps seamlessly. We could map operations, convert or normalize data, filter operations to remove or corrupt entries. Then we can validate and store the clean data in use models. Let's look at our second case study, parallelizing weather simulations. Functional programming also enhances simulation performance. Traditional simulations can take hours or even days due to interdependent tasks and shared memory. In contrast, functional codes, immutability, and their lack of side effects make it hard for parallelizable. We can divide data into chunks and process each chunk independently and then combine the data. In our third case study, machine learning model training. It's increasingly important in meteorology for storm prediction, climate analysis, and more. Functional programming allows us to build efficient, clean data pipelines for training these models using map to create features for raw input data to reduce, aggregate, and summarize data. Some benefits are easier testing, simpler debugging, and effortless scaling. Now let's talk about the future, open source, and community. Community-driven development is crucial. Meteorology, like many scientific fields, thrives on collaboration. By leveraging open source functional libraries, we can share models, tools, and pipelines with others around the globe. This not only accelerates development, but gives access to powerful forecasting tools, improving resilience and preparedness worldwide. In conclusion, functional programming offers 10 times faster development thanks to reusable, testable code, 99% increased accuracy by reducing bugs and unintended behaviors, 2 times better scalability, especially for parallel and unintended computing environments. The future of weather forecasting is not just about better models, it's about better code. Let's embrace functional programming and build a clearer, more accurate forecast together. Thank you.